At the foundation of any operating system is the process. Think of it as a strictly defined, isolated container of execution. The OS sets up this container to securely hold everything a program needs to run: its allocated memory, its data, and its compiled code. Modern applications, however, are rarely doing just one thing at a time. A web browser needs to fetch network data, play an audio stream, and render a user interface simultaneously. If we model this process container, we can see the structural problem with trying to run all three tasks at once inside a basic single-line architecture. A single CPU execution line physically cannot process them concurrently. It has to execute a piece of the network request, jump to the audio stream, jump to the UI, and then loop back. The execution stutters and lags at every jump. Forcing a single process to handle simultaneous tasks sequentially creates a bottleneck. Response times spike and CPU utilization drops because the processor spends its time switching contexts instead of computing. In order to achieve true concurrent execution, we must divide the workload into smaller execution units called threads. But dividing the code is only half the solution. Creating threads is useless unless the operating system kernel is explicitly integrated to manage them. The brute force method for solving this bottleneck is to simply spawn multiple, entirely separate processes for each task. An operating system enforces a strict rule. Processes require completely isolated memory. A rigid boundary separates them. Sharing data across that boundary forces the CPU to perform a context switch. Tearing down one environment and loading another is computationally expensive and slow. We bypass this bottleneck using threads. A thread is the smallest independent sequence of instructions, living entirely inside the process container. By sharing this container, threads bypass strict isolation. All tasks now read from and write to the exact same central memory block. This shared architecture immediately drops the overhead. Internal communication between threads happens almost instantaneously, as the data is already universally accessible. Furthermore, a context switch between threads requires a fraction of the computational power compared to switching between processes, because the shared memory space never has to be swapped out. Threads easily solve the memory overhead problem, but placing all these threads inside a single container creates a critical blind spot for the operating system, which schedules when threads actually run. To see this blind spot, we have to split the system into its two distinct environments: user space, where the applications and libraries operate, and kernel space, the restricted core where the OS hardware management occurs. The threads we just created exist entirely in the top layer. These are user-level threads. Because they are managed by user libraries, the OS doesn't know they exist. This makes them incredibly lightweight, switching rapidly without OS permission. The system runs smoothly until one user thread waits for an external event, like a network download pause. The OS only sees the outer container. Assuming the entire program is stuck waiting, the OS freezes the entire process. Even if the audio and UI threads are perfectly ready to execute, they are entirely blocked. Concurrency dies. The alternative is moving execution control down into the OS itself, using kernel-level threads. Here, the OS schedules every thread independently. If the network thread blocks, the OS simply switches focus to the audio thread, achieving true parallelism. But direct OS intervention requires higher system overhead. Spawning and tracking these heavy kernel-level threads slows down creation times and consumes significantly more memory. We are left with a direct trade-off. User-level threads offer speed, but lack the robustness to survive a blocked operation. Kernel-level threads provide true parallelism, but require significant system resources. Resolving this requires mapping the two together to leverage the strengths of each. Multithreading models are the architectural blueprints used to bridge the boundary between fast user space and parallelized OS hardware. The most basic approach is the many-to-one mapping model. This model funnels multiple fast user threads into one single kernel thread. It is highly efficient to implement, but it instantly fails the parallelism test. Because they all rely on one kernel thread, if one user thread blocks, the OS blocks the single kernel thread and the entire application halts. To solve the blocking issue, we can use a one-to-one mapping model. This model links every single user thread to its own dedicated OS thread. Parallelism is guaranteed. If one thread stalls, the others continue uninterrupted. While this is the standard used by Linux and Windows, it leaves a heavy footprint. Spawning a heavy, resource-intensive kernel thread for every minor, lightweight background user task aggressively consumes vast system memory and processing resources. The optimal solution for high-performance applications is the many-to-many, or hybrid model. It relies on a dynamic routing matrix, allowing a vast array of lightweight user threads to share a smaller, flexible pool of kernel threads. If a user thread makes a network call and blocks a kernel thread, the matrix instantly reroutes the remaining user threads to the available kernel threads in the pool. True concurrent execution is maintained, and system resource usage stays highly efficient. Selecting the correct mapping model is what allows an application to maintain smooth performance, even as its internal task volume exponentially grows over time. With a hybrid mapping model structurally supporting the system, lightweight threads can move rapidly and concurrently through shared memory. The execution data flows in parallel streams, completely avoiding the harsh stops and context switches of isolated processes. At the macro level, the benefits are immediately obvious to the user. Applications execute faster, CPU processing power is maximized, and user interfaces remain responsive even during heavy background processing. But this optimized architecture introduces a severe, unavoidable trade-off. The foundational reason these threads run so fast is their lack of memory isolation. They all pull from the exact same central address. If two parallel threads attempt to write new data to the exact same shared memory address at the exact same millisecond, the logic collapses. The system doesn't know which instruction to prioritize. This specific catastrophic collision is known as a race condition. Unregulated data sharing across threads inevitably results in corrupted files, frozen application states, and permanent system deadlocks. Breaking down a process into threads solves the performance bottleneck, but it creates a volatile environment that demands rigorous, deterministic synchronization protocols to prevent system failure.